So, the SINR is given by the expression here. We compared it with a narrowband system such as GSM, where the impairment would be colored noise, whereas in this case it starts to with the based on the central limit theorem, a large number of users, the impairment looks Gaussian. Okay. Then we sort of gave an intuitive view of what happens if one of the users is transmitting with more power than they need to. So, one of the questions during the break was, what do these lines mean? So, basically if you look at it as a function of frequency, what is your power spectral density? White noise means it is white, flat, it is present there. Because of your large spreading factors, all of your user signal also looks like white noise, but they add to the noise. So, basically as you add more and more users, the noise floor seems like it is rising. Okay. That is the way to visualize it. Now, if one of the users is transmitting with more power, they would raise the noise floor by a much higher amount than the other users. Now, where will it affect you? When you start despreading the users. When you despread the user who is transmitting with more power, it does not affect that user at all. So, basically you can see that the green user is fine, but when you detect the other users, you will pay the penalty, and that is exactly what we find in the near far problem as well. So, basically this is a manifestation of the near far problem, and it comes from the fact that the users with transmitting with more power than they need to actually raise the interference floor. We mentioned that the best scenario, best performance that we can hope to achieve is the single user bound, and usually as the number of users increases, you will find that the BR degrades. Of course, you want to make it as close to the single user bound as possible. Near far problem, we can relate it in terms of the SINR and the degradation that you are going to see for that particular user. And we showed with the case of two users, if one of the users is much stronger than the other, then that is an undesirable situation for us in a CDMA system. And what you will end up doing is user 2 will get detected without any problem, user 1 will get affected because of the presence of user 2, and of course that told you how to jam a CDMA base station. Okay, now we move into a very interesting component which is called CDMA capacity. When CDMA and TDMA were sort of competing with each other, the arguments always was which system had more capacity, and always the argument was CDMA systems have more capacity. And what were some of the ways in which they were looking at the capacity of a CDMA system? The following is the way. Capacity of CDMA systems. Okay, very interesting discussion, very interesting perspective. So, we recognize that in a CDMA system, interference can come from within your own cell and from outside. So, the more dominant one is this interference coming from your own cell. We call that as intracell interference. Intracell interference. Okay. We will use the term IC subscript, intracell, and this is approximately equal to K minus 1 by Q times EB, assuming ideal power control. And we are going to make an approximation. This K minus 1 is small compared to Q, so this is the same as K by Q times EB. That is just easy for us to work with, minus sign. So, we also recognize that that is intracell interference. Neighboring cell, neighboring sector, all of them are using the same frequency. Neighboring cell, neighboring sector, all are using the same frequency. So, which means using the same frequency, which means they are all generating interference. Ultimately, all of this is going to affect the performance of my system. So, the total interference which is in a cellular system, which is a multi-cell system, you have to take into account what interference is being generated by the other cells also. This is a multi-cell system. Okay. So, I naught is the total interference this will be I intracell plus I other cell. So OC other cells, indicate that OC stands for other cells. Okay. Now, in order for us to put a get our arms around the interference environment, we make the following assumption. Assume that the total interference coming from other cells can be some fraction of the intracell interference, and alpha, if you have a good system design, should be somewhere between 0.5 to 0.6. Your own cell is creating a large number of amount of interference, because every user is there is power control issues, all of them are present. So therefore, there is a certain amount of interference that is coming from your own cell. All the other cells put together create an interference which is also significant, but not as much as your own cell interference. So the total interference can be classified as 1 plus alpha times I intracell interference, and this is nothing but 1 plus alpha times K by Q times EB. That's from equation 1. I have substituted that expression. Okay. In a CDMA system, we are always interested in SINR of the user. So SINR of the user is given by EB signal component, N0 AWGN component by plus I0. I0 is the total interference that is present in the system, I0. And several interesting ways in which we can interpret this result. So I will do a series of expressions, each of them will add some more insight into our understanding. I am going to do the first of those expressions. I am going to factor out I0 in the denominator. I0 then becomes 1 plus N0 divided by I0, that is equal to EB, and I0 is given by 1 plus alpha K by Q EB 1 plus N0 by I0. Okay, that is one all these are equivalent expressions for SINR. Interesting, EB will cancel. So this will give me 1 divided by 1 plus alpha K by Q 1 plus N0 by I0. Something seems wrong in this expression. How can you get SINR without EB in the picture? I0 has got the picture. There is some term in the denominator, EB did not go away, it is still there, do not worry, not explain. Now comes another very interesting unique feature of a CDMA system, and if you have worked with practical systems, you will really appreciate this. Something called voice activity factor. Okay. Those of you who have friends who are working in speech, or maybe you yourself are working in speech, you know what is voice activity factor. When A is talking to B, if you monitor the conversation, at any given point only one person is speaking, the other side is silent. And actually if you look at studies, there are lots of times when neither of them is speaking. I think both of them are thinking. Okay, so what to say next? So there is actually there are idle times. So then in a GSM system, what happens? A is talking, B is not talking, but there is a link provided for B to A. What does that link do? That's not doing anything. It's just idle. It's just basically transmitting maybe some background noise. So voice activity factor is a very interesting phenomenon. Now in a CDMA system, if you don't have anything to transmit, what will you do? You can transmit with low power, because you don't have anything to transmit. So basically you will transmit very low data rate, which you will spread by a large spreading factor, and you will transmit at low power. So voice activity factor typically is in the range of 0.4 to 0.5. We use the Greek symbol nu for that. This is typical for speech, And if there is no transmission or no need for either you transmit very low rate or you do not transmit anything at all, either way what will happen, your signal is not causing as much interference to others, right, because your signal has, power level has gone down. So the SINR with voice activity factor, so SINR with voice activity factor, this is very unique to CDMA system. In a GSM system, whether you have a voice activity factor or not, it does not make any difference, your signal is not affected or capacity is not affected. Here the capacity will get affected. 1 plus alpha, that voice activity factor, because if you only 0.4 of the time is present, that means k users 0.4 of the time, right. So k times nu. So nu times k divided by q, directly it is affecting your into 1 plus n naught by I naught. Okay. This is a major advantage of a CDMA system, major advantage of a CDMA system, and it is not there for the narrowband systems. Okay. Again, if you want to go back and look at the expression, basically what we are saying is intracell interference we said was approximately k by q times EB. If voice activity factor is incorporated, becomes nu, so which means your intracell interference went down almost by a factor of half. Okay. So in intuitive terms, you can load your system double, because only half the users are active at any given time. So if you have a capacity of k, you can actually load it up to 2k, because only half the users are going to be active at any given time. So again, so this voice activity factor is plays a very important role in our system. Okay. So typically in any CDMA system, the role of power control and the role of system design is you want to achieve a certain target SINR, and the goal is every user must be able to have the same SINR so that you can get good performance for each of the users. So the target SINR, maybe you want to write a T or there, something for target, is given by EB by I naught plus N naught. This is the same as EB divided by 1 plus alpha times nu times k by q EB plus N naught. Okay. Group the EB terms together, you will get EB into 1 by SINR target minus 1 plus alpha nu k by q, this is equal to N naught. Okay. The energy level with which you must transmit that particular user signal is given by N naught, your noise variance, that's a constant that is known to you, divided by 1 by SINR T minus 1 plus alpha nu k by q. This is a very, very important equation that we work with. So the power with which you must transmit a particular user signal under the assumption of ideal power control is given by this expression. Now very intuitive to understand what is the links between these two. If N naught increases, that means your noise floor, your signal noise figure, your receiver noise figure is bad, so your N naught goes up, EB has to go up. Okay. If you say that my SINR target has to go up, SINR target has to go up, okay, so you will find that EB has to go up. That's the only way you can meet that. If the number of users goes up, then your denominator becomes smaller, so therefore EB has to go up. If your spreading factor becomes smaller, then EB has to go up to compensate for the reduction in spreading factor. If the interference from other cells goes up, again EB has to go up because you have to compensate it in your own cell. So you can see that all the factors that are around you and see how it links to EB. Okay, very important. This is one of the key concepts that we're now going to introduce another unique concept. Just like voice activity factor, there's another very unique concept. I'll write the concept name later after we have described the concept itself. The total interference in a CDMA system is given by 1 plus alpha k by q nu times EB, right? 1 plus alpha, alpha is the other cell interference, k is the number of users, q spreading factor, voice activity factor. Okay. SINR is always EB divided by I naught plus N naught. Okay. One maybe sort of trivial observation, but it is important for us. Let me just write it down. If I naught goes down, what happens to your SINR? SINR goes up. Two things you can do. One is, of course, you can, if you want to maintain a target SINR, so for target SINR, you can reduce your EB, that is one. Another thing you can do, what is that? If your I naught goes down. So think of it in terms of a system. This is my base station. I have a nominal capacity, nominal coverage radius, okay, and this is my nominal boundary. If I transmit at this from this place, I will reach the base station under the assumptions of the interference. Now I naught has come down, then what happens? I can either at the boundary I can transmit with less power, or if I am willing to transmit with the same power level, what is it? I can go further away from the base station. Okay, that is very, very important. So there is a boundary which is larger than my nominal boundary when the interference reduces. Okay, so this is the boundary under low interference or low load. Low load meaning a fewer number of users are in the system. The corollary to that, if I have more users than I have planned for, my boundary is going to go shorter. It's going to look like only these people can communicate with my base station. Okay. So this is the boundary under high load. High load. So this is another very unique feature of a CDMA system, which is called cell breathing. See, when you breathe, your lungs go in and out. So just like that, if interference increases, the coverage decreases, and when the interference reduces, the coverage increases. So this is the concept of cell breathing. So you can not have a fixed boundary for a CDMA system. It is something that is going to vary based on the load, and it's a very important concept that is we can take advantage of. Okay. Now this is the reason why CDMA is very, very attractive for rural deployment. Very attractive for rural deployment. Why is that? One is there are not too many cells, so other cell interference is not much is present, and if the number of users is small, you can have a very large cell. So one base station will cover several kilometers, square kilometers of. So very attractive for rural type applications. Rural deployments, also if you have a single cell deployment, rural or a single cell deployment, it has very, very attractive properties. Because see, if I were a GSM system, if I were at the boundary, whether there is other users present or not, I have to transmit at the same power level. Whereas here, if other users are not there in the system, I am the only one in the system, I can transmit with much lower power and I can conserve battery. So which means that there are certain advantages of a CDMA system in terms of the battery life and power, all of that becomes an important element. Okay. Now comes the asymptotic case. Asymptotic case always very interesting. What happens if I keep on adding more and more users into the system? What will happen? That red circle will keep shrinking. Eventually, what does that mean? You cannot be outside of the red circle, you have to be inside the red circle. If the red circle keeps shrinking, 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 eventually what happens? All of you are around the base station, everybody has to be around the base station. That is called pole capacity. So, pole capacity is the asymptotic capacity that you can achieve in a CDMA system. It has no use because everybody is standing next to the base station, but it is an asymptotic limit. So, basically it is as k increases, only users closer to the base station, only users who are close to BTS can communicate with the BTS, right, close to BTS can communicate. That means that red circle is shrinking, BTS can communicate, and in the limit it will be all the users who are around the pole, that is called pole capacity. Okay, pole capacity tells you that you cannot exceed pole capacity, that is the maximum that you can achieve in a CDMA system. So, there is a number for the pole capacity, and we will write that down. Pole capacity, useful for us to write it down in terms of 1 by SINR. Again, it is easy for us to visualize this. 1 plus alpha times nu k by q plus n naught by E b, okay, and 1 by SNR. That means usually if SNR is a reasonable amount, you have designed your system to have 1 by SNR, this is nothing but 1 by EB by N naught. So, this is a small quantity. So, we will say that we will neglect this in the asymptotic case, only the interference is going to dominate, your noise is not going to dominate. So, what does this one say? That the pole capacity, so maybe we should write a k subscript pole. Okay, under pole capacity, noise is not an issue, all we have to worry about is the interference that is being generated by the system. So, let us see what this number is going to be. If q is equal to 128, that is my spreading factor, my target SINR I want to achieve a 6 dB, so that is equal to approximately 4. Other cell interference is 0.6 factor, the voice activity factor is 0.45. I want to estimate what is k pole. Basically substitute, it will be q divided by SINR into 1 plus alpha times nu. This will come out to be 44.4, which is the same as 44 users. Okay, interesting. What are the assumptions? Q is equal to 128 spreading factor. I probably have 128 spreading codes available, large number of spreading codes, but I cannot achieve 128 users in my system. Why? Because there is non-idealities in the system. I also have other cell interference. All of that is going to play an important part in my system. Now, another very interesting observation, if I had not exploited voice activity factor, so like a system like GSM which cannot exploit voice activity factor in capacity, without voice activity factor the pole capacity would have been 20 users. So, voice activity factor plays a huge role in a CDMA system, it almost doubles the capacity of a CDMA system. Okay? But at the end of the day, we are all good engineers. We ask the question, what is the practical capacity? Of course, it's not 44, it's something less than 44, but how much less than 44? So, this is where our understanding of the CDMA interference comes into play in a very, very useful manner. So, practical capacity of a CDMA system, practical CDMA system. So, the first assumption that you say is, hey, do not give me this pole capacity business because there is no use. That means I have to have what infinite number of cells, no use, no coverage at all, everybody is at the base station. So, I need to have a finite cell radius, finite cell radius. So, in other words, I cannot let interference completely dominate the show, I have to limit it. So, one way that we can limit it is go back to our drawing of the power spectral density. If this is noise level, do not let interference keep on rising. We just say, okay, there is an upper limit on the noise. This is the upper limit at which the I naught. So, this is I naught. this level will be N naught plus I naught. So, basically you put a upper limit to which the noise, the interference. So, this is called the noise rise. So, there is the AWGN and then the interference goes on increasing the noise. So, that is called the noise rise. So, the total noise rise, noise is actually interference, but we refer to it as the rise in the noise floor. This is given by N naught plus I naught divided by N naught. So, we say that this can be, for example, this is an example 6 dB. Okay, this is just an example. You could have chosen it to be 5 dB, you could have chosen it to be 10 dB, but each of them has got implications. If you say 10 dB, that means that noise interference will be, more interference will be allowed into the system, your cell radius is going to shrink. So, you have to play that, you have to be careful about that. So, we say 6 dB is usually a very good number for a practical system. So, this is an example. Okay. So, 6 dB is nothing unique about 6 dB, it is something that you will have to choose as a designer. So, this is nothing but 4, this is equal to 4, 6 dB is nothing by 4. So, it says I naught plus N naught is equal to 4 times N naught, or I naught is equal to 3 times N naught. So, the total interference that you will allow in your system is going to be bounded by 3 times N naught. You are not going to arbitrarily allow the interference to increase. So, under this assumption, the capacity will now be calculated. Okay. So, SINR is equal to EB by N naught plus I naught. N naught plus I naught is 4 times N naught, EB by 4 times N naught, or in other words EB can be written as 4 N naught times SINR, 4 N naught times SINR, and we will just see in a moment why that is useful for us. So, I naught, the total interference, is given by EB into 1 plus alpha nu divided by Q into K. That is the expression for the total interference. I naught is equal to 3 times N naught, EB is equal to 4 times N naught from equation, call this equation 1. So, from 1 is equal to 3 times N naught times SINR, 1 plus alpha nu divided by Q into K. Okay. N naught will cancel on both sides, K is equal to 3 by 4 Q divided by 1 plus alpha nu by SINR. Okay. Interesting interpretation. What is this quantity? That is pole capacity. Pole capacity. So, the practical capacity is a fraction of the pole capacity. It is a fraction that is less than 1. And what determined this fraction? The noise rise. So, this is a fraction less than 1 that is determined by the noise rise. If I allow more noise rise, I will have a larger fraction, that means capacity will increase, but my radius of coverage will decrease. So, therefore, we will be, so in the previous example that we calculated, if I set a 6 dB noise rise, then this will result in practical capacity. Practical capacity is 3 by 4 into 44, which is 33. Is 3 by 4 into 44, which is 33 users. This is still a very good system because it is able to support a large number of users in a multi-user environment and achieve very good capacity and all the benefits that we have claimed for CDMA. Okay. Any questions on capacity calculations? How do we estimate practical capacity? How do we estimate the pole capacity, and what are the impacts of these quantities? Any questions? Okay. Now comes another question that I want you to think about and answer. When we talked about handoffs, in a CDMA system we said there can be something called soft handoff. Do you recall what soft handoff is? One mobile talking to two base stations, correct? Okay. So, I just want to spend 1 minute on, so soft or softer does not matter, basically both of them have the similar, okay. At that time we made a statement which said that soft handoff is not good for capacity. So, since we have already talked about capacity, we need to justify that statement. So, if this is my base station and my mobile is in the border of two sectors, I can talk to the mobile through sector 1 and I can talk to the mobile through sector 2. Okay. So, both sectors are communicating. So, this is actually softer handoff. That doesn't both sectors are communicating with the mobile station, Now, since two base stations are listening to the mobile can actually transmit with less power, correct? Can transmit with less power. Now, if I transmit with less power, capacity should increase. Why is capacity decreasing? You agree, no? Transmit with less power, it's going to, overall interference is going to go down, capacity is going to increase. So, basically this is a scenario of macro diversity, right? Two base stations are listening to the mobile, both are transmitting. So, therefore, the mobile gets good signal, the base stations are the mobile can transmit with less power. Okay. What is the, why is the capacity going down? The capacity is going down because you are using a code in sector 1 and a code in sector 2. The capacity is not going down because of the interference you are generating, its capacity is going down because of the number of available codes. Okay. So, capacity, you can of course achieve a certain capacity in each of those sectors, but if your codes are not present, basically you used up your codes. So, capacity is reduced because of available codes, available number of codes. Okay. Because what happens is each of these mobiles, there will be several of these mobiles that are on the border of the sector of the cell of coverage. So, which means that all of them will want to go into soft handoff. The minute you have large number of mobiles going into soft handoff, yes, they are not generating much interference, but they are actually using up codes in your system. So, that is where the capacity comes from, impact comes from. So, soft handoff is very good in terms of robustness, it is very good in terms of signal quality, but not so good in terms of the number of codes that it uses, because each of these it's using one code from each of the cells that is talking to. And of course, you can imagine that if the mobile moves to a boundary of another slightly different location, it may actually be in soft handoff to three sectors. So, which means you're using resources from 3 sectors. So, again mobiles love it, but the system does not like it so much. So, it says okay, no, always limits the number of soft handoffs system. So, given this scenario, the capacity of a CDMA system, okay, you can visualize it as noise rise, you can think of it as codes available. Capacity of a CDMA system very different from a TDMA system. TDMA system is very simple to calculate capacity. I have 8 time slots, what is the capacity? 8 users, there is nothing, no, I cannot go to 9, so basically it is fixed. But in a CDMA system, there is no fixed number. Why? You can say that the voice activity factor instead of 0.4, it is 0.39. What will happen? Your capacity will increase. If you a slight tweaking of the parameters will change your capacity. So, it is one of those systems where we say that the capacity of a CDMA system actually has the property of soft capacity. Okay, it is not a hard number. it is something which depends on a number of factors, how much interference you are getting from other cell, how good is your power control, how good is your voice activity factor exploitation. All of that, if you assume ideal, then you get a number which is very, very large. Then you start to look at practical assumptions, and then you put a limit, and then you compare with the capacity. So at the end of the day, you still have one more parameter to vary, and that parameter is your size of your cell, because of cell breathing. So again, the number of capacity of a CDMA system can never be quantified easily. It's a soft capacity. You can always increase, you can add one more user to the CDMA system with a slight penalty for everybody. In a GSM system, that is not possible. You've reached 8 users, that's it, no more, 9th user is blocked. Whereas in a CDMA system, you have basically an understanding of soft capacity. Any questions on capacity? Because this is a very, very important concept. It tells you what is the difference between a CDMA system and a TDMA system or any other system. So basically, the last part of our discussion on CDMA systems, again, I wanted to make sure that whatever you have studied in digital communications kind of ties in together. So we will look at CDMA receivers more closely. CDMA receivers. So basically, multi-user detection receivers. Where do you need multi-user detection? It's at the base station. So multi-user detection, what are our options in terms of the different receivers that we know from digital communications? How do we apply them, and what is the complexity that we are talking about? Because as I mentioned to you, CDMA systems are far from trivial. One is because you've got all these M sequences, the long code, short code, all of that. But even if you overcome all of those hardware challenges, at the end of the day, to actually be able to detect the signal is non-trivial. So the first thing that we would like to look at is, what is the optimum receiver for multi-user detection? Again, we will look at a simplified problem, because the full complex problem is harder, but this gives us enough of a insight into the system. So the multi-user figure that we have drawn earlier in the lecture, please keep that picture in mind. So it is synchronous transmission, uplink, synchronous transmission, and we will assume that the channel is AWGN channel, so no multipath. It is an AWGN no multipath, made it as simple as possible, and even for this, the receiver is so complex that it would be hard for us to implement. Let me justify that statement. So at a given time, each of the k users will transmit a bit. User 1 transmits B subscript 1 1. The one within brackets is the time index. The subscript is the user index. B2 1, BK 1. Okay. Since all of them are transmitted at the same time, I need to be making a decision on each of those B1 through BK. So the received signal R of t is given by summation k equal to 1 to uppercase K, Bk of 1 root Ek, that is the level, the signal constellation scaling, times Gk of t plus Z of t, right. Gk of t is a spreading sequence, a spreading waveform, and okay. Very quickly, let me remind you that the optimum receiver for us is the maximum likelihood receiver, and the maximum likelihood is described as follows. It's that receiver that will find the sequence or the vector B, hat is the estimate, that minimizes the probability of error. So the most likely sequence that was transmitted, that minimizes the probability of error. probability of error. That is the criterion that we are using. So, in other words, to say it in a more formal manner, it is to choose that b hat equal to some vector b1, which for which the probability of r given b1 is maximized. b1 is a vector. Okay. That is the statement. So, you basically want to find out that vector of values which gives you the most likely probability of receiving the vector r or the received signal r that you have obtained. Okay. It is not a complex statement. Basically, it says if in a 2-dimensional case, if this was r, okay, and if one combination of vectors, let me call that as some b dash, says that the if you use b dash, this is where you will, this is what your r vector will be. Another thing says, okay, this is b double dash and b triple dash. Okay. So, each of these 3 vectors or combinations says, okay, this is where you would have, this is what r would have been had you transmitted b hat. So, you look at these 3 combinations and say, well, you know, this is the one that is closest in Euclidean distance, and therefore, my b hat I am going to declare to be equal to b dash. That is maximum likelihood detection. So, you look at all combinations of vectors that are possible. For each of them you construct r and then see which is the one that is most likely to have occurred. Okay. So, here is the problem statement. You have to minimize over all possible combinations of the vector b. Vector b, since there are k and it is binary, there are 2 possible k choices that are possible. You have to look over all 2 power k choices, that is the minimization step, and you have to look at the following the objective function. So, the objective function is minimize over all b such that the integral from 0 to t r of t, that is the received signal, minus the constructed signal for the combination of transmitted bits, k equal to 1 to uppercase k root e k b k no b1, sorry, b1 of well, I have to be careful with my notation here. B, okay, I have used k, okay, b k of 1 g k of t magnitude squared dt. So, for every choice of b, I have to, this is like saying this is what r hat will be if I use this particular transmitted vector of bits. So, you are looking at the Euclidean distance between r of t and r hat of t, and it is not strictly Euclidean distance, it is actually the distance squared and integrated. So, basically you are looking at the squared distance from the received vector to the reconstructed vector. Okay. You have to consider all 2 power k choices. So, some observations about the ML is that it is exponential in terms of the number of users, exponential in number of users. Okay, that itself is a source of complexity. Now, if you do non-binary, it is even worse, because then it becomes not 2 to the power k, but it becomes m to the power k. So, there is a very rapid growth in complexity. Rapid growth, if k increases or if your constellation size increases, both of them will cause exponential growth in capacity. So, obviously, this is a system that is complex. It is the best, but it is going to be very complex. So, let us see how to get a little bit more insight into the system. So, the objective function gamma of a particular vector b, this is given by integral 0 to t r of t. Basically I am expanding the term within this, this will become r of t magnitude squared dt minus integral 0 to t 2 times real part of summation k equal to 1 to uppercase k root e k into b k of 1 g k star of t times r of t dt, and then there is a third term which is integral 0 to t, basically the term and its conjugate. So, it becomes a double summation k equal to 1 to uppercase k summation m is equal to 1 to uppercase k square root e k square root e m b k of 1 b m of 1 g k of t g m star of t dt. Okay. So, basically whatever was within the modulus squared, I have expanded it out. Okay. Again, this may look messy, but the insights are there in just one step. Basically I am going to define, I am going to make certain observations about this. So, when I take r of t, the received signal, and pass it through a waveform, correlate it with the waveform of user k dt, I am going to call this as r subscript k. That means received signal correlated with the kth user's spreading waveform. So, this can be thought of as the output of a correlator receiver, okay, output of a correlator receiver. Then another one comes from this term, where it is a integral between 0 to t g j of t g k star of t dt. I am going to define this as a correlation coefficient between the waveform of user j and user k. K is the one that I am using to detect. So, first subscript is the waveform that I am using in the detector, and j is the user's spreading waveform. So, this is a cross correlation between the spreading waveforms of user 1 and user j and user k, user j and user k at the waveform level. Okay? And I can write down a cross correlation matrix, which is basically these correlation terms, and you can also verify that rho kj is the same as rho jk, because we are using real waveforms. So, because of the real waveforms. Okay. So, I basically get a correlation matrix which is symmetric, which has certain symmetry properties. So, this expression can now be rewritten as follows. The first one I retain as 0 to t mod r of t whole squared dt, making the observation that no matter what b I choose, this term does not change. This is always a constant, and no point in keeping this constant. I am going to drop this constant in the next step. But before that, this term, this middle term, can be rewritten in terms of the quantities that we have just now defined. This can be written as B Hermitian times Rk minus Rk Hermitian times B when you have both those terms, you will get the real part. And again, if you make sure that you look at the expressions, you should be able to get this one. The last term can be written as B Hermitian R B. Okay, I am going to drop the first term and retain only the terms that are remaining. So basically, what am I trying to do? I am trying to minimize over all possible B. The same problem can be rewritten as, leaving out the first term, it can be written as a maximization over all B of the following, of B Hermitian times Rk minus plus Rk Hermitian times B minus B Hermitian Rb. Okay, so basically it is leaving out the first term, whatever is left, I took out the minus sign, so minimization became a maximization. So this is what we have to work with. This is the optimal receiver. We have not made any change. So it's very interesting to see what is it that we need to do to implement this. So you take R of t. It's very intuitive. The result is interesting. So I correlate with G1 star of t, and followed by an integration from 0 to t, and then sample it, and this output will be R1. Same R of t I multiply by G2 star of t, followed by an integration from 0 to t, this becomes R2. And the last of the correlators, G subscript k star of t, followed by an integration sampling, this becomes Rk. So this is how you would generate all the Rks. So you take it into a block for which you have fed in all the Rks, all the different combination of B's you feed in to this one, and what does this term already need to know? It should know what R is, basically the cross correlation. That is a pre-computed R is already present inside. So based on this, you can then say which is your best B hat by applying this equation, by applying A. So you, for any R, you calculate R1 to Rk. You have to try all 2 power k combinations. 2 power k combinations you have to try and decide which of them gives you the maximum value. Okay? So let me just give you one example for you to try, and then we'll close with that. The example that I want you to try is a simple 2-user case. 2-user synchronous CDMA case. And this is the following information that we have. The received vector from the correlation of the two, so basically R1 and R2, this comes out to be minus 0.08 minus 0.47. So in the absence of any other decision mechanism, what you would do, you take R of t, you correlate with the waveform for user 1, then you take R of t, correlate with user 2, and you get these two values. If you now say make a decision on this, the simplest way is, okay, if I got minus 0.08, the decision should be in favor of a minus 1. So this one I will say the transmitted symbol was a minus 1, this one also the transmitted symbol was a minus 1, because what did I do? I took the received signal, I correlated with R1, this waveform of user 1, assuming that it has suppressed user 2, I got a value of minus 0.08, which I have to map to minus 1. Similarly, I do this. Now the optimal receiver says, hey, this is good, you got this information, but you totally forgot about the cross correlation between the waveforms. They were not ideal. So the cross correlation is given to us as following: 1, 0.33, 0.33 and 1 is symmetric. It's okay, and we also said you can assume E1 is equal to root E2 equal to 1. There is no difference in terms of their constellations. Okay, the possible sequences are 1, 1, 1, minus 1, minus 1, 1 and minus 1, minus 1. 4 possible combinations are there. You would have to try all of those. So, for each of them you try B Hermitian times R plus R Hermitian times B. Basically, you will get scalar values for each of those. Then you have B Hermitian R B. Okay, so you know what R is, you know what B's are, you can substitute and you can verify. So these values for the 4 vectors that we have used come out to be minus 3.76. Please, I request you to verify that. Minus 0.56, minus 2.12 and minus 1.56. You please use this value and do it. Okay, and I am trying to find the maximum, and I am interested in doing the maximum. In this vector, the maximum is minus 0.56, the others are all more negative, and this corresponds to 1 minus 1. So actually your original decision was not correct. The maximum likelihood receiver says it is 1 minus 1. And why did you make a mistake in the original one? In the original case, you did not take into account the interaction between the spreading sequences. You assumed that the spreading sequences were perfect and did the suppression perfectly, which it did not. So therefore, a maximum likelihood decision is going to give you in some cases a very non-intuitive decision, but that is based on the interaction between the spreading codes. Okay. So I just have sown the seed for what is the optimal receiver. It is definitely not what you would do intuitively, because intuitively just says correlate with user 1 waveform, put a threshold and say it is a plus 1 or a minus 1. No, 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 you have to take into account the interaction between the spreading codes, and that is going to make. Now the question that we then ask is, well, this is too complex. I mean, even for the 2 user case is non-trivial. So how do we make it into reasonable complexity? Okay. Now from a maximum likelihood type of scenario, the next lower complexity but reasonably good performance is something called zero forcing receivers. Okay. We will look at what is a zero forcing receiver in the context of a CDMA. Zero forcing receivers have got a drawback in that they do not care about the noise. The noise may get boosted in the process of getting a zero forcing. So what is the best which does not boost the noise? MMSC receiver. So you have ML, zero forcing, MMSC. All that you have studied in digital communication sort of comes together to say, oh, this is the complete way of handling CDMA receivers. So the ideal receiver for us is an MMSC receiver, which is good in terms of complexity. But in order to appreciate the MMSC receiver, it is good for us to have started with the optimal receiver, to talk about the zero forcing type. In the case of CDMA, it is not called zero forcing, it is called a decorrelating receiver, but essentially zero forcing, and the other term other type is the MMSC. So just part of the tomorrow's next lecture will be the decorrelating receiver, a part will be the MMSC receiver. With that, we complete our discussion on CDMA. We will move into the MIMO framework. Okay, thank you. See you tomorrow.